Shall we get started? So in yesterday's class, we saw about the Earth's magnetism, right? I hope you're able to see. Those who are online, are you guys able to hear me?
Yes, sir.
Okay. So listen, we will just recollect the points. So what is magnetic declination called as? It is defined as the angle between the geographic meridian and magnetic meridian, right? Or I also called it as the angle between the geographic axis and the magnetic axis. Now, what are the other types of magnetic Earth's magnetic elements that we are going to see? Just a minute. Okay. So, what is the relation between Earth's elements of Earth's magnetic field? So, if suppose we know the Earth's magnetic field is BE and the angle of dip is delta, right? I repeat, if the Earth's magnetic field is BE and the angle of dip is delta, then this BE can be resolved into two components which are called as B cos delta and BE sin delta. So this BE cos delta is called as BH and BE sin delta is called as BV, right? Which is called as the vertical component of the Earth's magnetic field. Then how is BE related to BV and BH? Root of BH square plus BV square. I hope this concept is also clear. Right, this also we have discussed. Similarly, if they give you the horizontal component and vertical component, it asks you to find the angle of the, how will you do it? So tan delta will be equal to BV divided by BH. I'm assuming that everybody has written all these formulae, right? So these three are the formulae that are related to the elements of Earth's magnetism, right? Now, having said this, we can try out few problems based on Earth's magnetism. See, for example, read this question. Okay. The declination at a place is 15 degrees west of north. Okay, I repeat it. The declination at a place is 15 degrees west of north. What is the meaning of this? What do you mean by west of north? Anti-clockwise from where? That 15 degrees should be measured from north. So it is not northwest, or don't you? Did anyone use the word northwest? I could hear it. So northwest means 45 degrees. West of north doesn't mean 45. It can be any angle. Okay. So west of north is 15 degrees. Is there anyone having doubt or confusion with this? Is everyone clear? Nathan? Everyone? Yeah. So this is north, east, south, west. Now read the question carefully. In which direction should this ship be steered so that it reaches a place due east? So the ship is supposed to be reaching east. According to the declination that is happening, it is already going in this direction. So if he has to reach this east, it is not 60. It is this 90 plus 15 degrees. Right? So it is 90 degrees plus 15 degrees, which is 105 degrees. So is it not like the zero error which I explained yesterday? So there is an error, right? So due to that error, what is happening? If they want to go to the east, then they need to steer it to a particular direction. Is it clear? Next. So I hope it is simple, right? So based on the same concept, can you guys try another problem? Right? 1 minute, I have to rub this first. So there is a ship which is to reach a place 10 degrees south of west. So the expected destination is where? It is 10 degrees south of west. Means third quadrant is okay. The 10 degrees should be taken with respect to whom? Read the question carefully. Anti-clockwise is okay. My question is the 10 degrees south of west is there, no? The 10 degrees will come with respect to south or west. Yes. It will come with respect to west. Whatever is the word after that of. So that is where you are making the angle. So 10 degrees south of west. Is that clear? Now, in which direction should it be steered if the declination at the place is 18 degrees west of north? So how did you get that? So there is a declination happening in the west of north, right? So how much is it? It is 18 degrees. So actually the ship is going in this direction. It is not going in the north direction, rather it is going in the, it is somewhere between north and west at an angle of 18 degrees. But what is the expected destination? It is exactly at an angle of how much value, guys? So this is 72. So 72 degrees plus 10 degrees, that is going to give you 80 degrees. So we need to steer it in the direction with an angle. So steer it in the anti-clockwise direction with an angle of 82 degrees. Means the steering wheel should rotate to 82 degrees. Is it clear? That is a geographic north and the geographic south. Pointer, yes. So this is the needle. This is the geographic north. That is not. So that is why there is an error. That's why it's called magnetic variation. So that is what I tried to explain you today. Yesterday. I told you about the fact that the geographic north and the magnetic north will never coincide. Is it clear? So maximum these kind of problems will also only come. If the opposite means it will go for reflex angle. Why would anyone take a longer? Right? So I hope problems are easy only, right? So read the question. This is also simple only. In the magnetic meridian of a certain place, the horizontal component of the Earth's magnetic field. So what is the given data? The horizontal component of the Earth's magnetic field is 0.26 Gauss. Is it right? And the angle of dip is 60 degrees. What is the magnetic field of the Earth in this location? So BE is equal to how much? Sorry, BH is equal to how much? It is BE cos delta. So B is 0.26 into. Wait. Sorry, BE. B is what you need to find. No, BH is 0.26 is equal to B into cos 60 is half, which implies BE will be equal to 0.52 G. What does G stand for? 1 Gauss is how many Tesla? Very good. 1 Gauss is 10 power minus 4 Tesla. So Gauss is Celsius unit, Tesla is the SI unit. Is it clear? So this one is not needed. Now we'll try the fifth one. The horizontal and the vertical component of the Earth's magnetic field at a place are 0.22 Gauss and 0.38 Gauss. Calculate the angle of dip and the resultant intensity of the Earth's field. Simple. So what are the given data? Horizontal component is 0.22 Gauss. Vertical component is 0.38 Gauss. Calculate the angle of dip. For the tan delta will be equal to BV divided by BH. That is 0.38 divided by 0.22. So 0.38 is 0.19 divided by 0.11, or this is equal to 19 by 11. So delta will be equal to tan inverse of. Is that right? So next one I've already written it. You are able to see the formula. So resultant intensity is root of BH square plus BV square. So 0.22 square plus 0.38 square. That will give you the answer. Those who are online are able to understand?
Yes, sir.
Can you just give me a confirmation at least in the chat box? Perfect. Okay. So this is all about Earth's magnetism, and we are done with the chapter. Okay. So I hope it was simple only, right? But yeah, you have certain confusing terms for which you definitely need to put in some effort to understand the magnetic field intensity, magnetization, all over nearby terms. But try to put in some effort and read it, you will understand. Okay. So apart from this, is there any doubt that you have? I hope this chapter is clear, right? So you understood what is the purpose of why we studied this chapter also, right? Is it G? 4.27 something. 0.47. Yeah. Right? So having said this, we are ready to get started with the next chapter. Shall we? Yeah. So write down the name of the next chapter, that is electromagnetic induction. So what is the chapter number? 6, and it is called as electromagnetic induction. Yes. Okay. Now listen to this introduction. See, thing is, if you had been seeing the chapters from the beginning, right? The first chapter is related to charges at rest. Second chapter was also related to charges at rest. But what was the difference we dealt in both the chapters?
Second has to be read more about potential.
So you were concerned more about the work done and the energy associated with the electric system, or I can say a system where the charges were at rest. Is that right? So in the first part, you were concerned about what is the amount of field that the charges or the system of charges were able to create. In the second chapter, we were concerned about when you do some work on the system or the work is done by the system, how much amount of energy is going to get stored, which out of which both are important. Apart from that, in the last part of the second chapter, we understood you have something called as a capacitor. So why did we need a capacitor in the first place? Because till then we understood that charge is existing. But the next question is, where will you store it? Right? If you keep it just like that, it is lost to the surroundings, right? So we read about capacitors. So by now we know the fact that capacitors are those devices which can hold charge. And they have something called as capacitance associated with them. It's a property. Right. So on the other end, if you put the same charges into motion, right? If you need to put the charges in motion in an aligned path, you need something. What is it? You need a potential difference. So that potential difference will do some work on the system, and it will make the charges move. Out of which we could generate some useful amount of work. If you see, every chapter has a purpose, right? So in current electricity, what were we using? We were making use of the heating effects of electric current. That's what we use in many devices. No? You think about an oven, or you think about an iron box, you think about iron, okay, whatever it is. Kettles. So I wanted to talk about the straighteners and all those things. Those also use the heating effect of electric current, right? So it had some purpose. Then came the next concept. Okay, if electric current. So we understood from the first chapter that if the charges are at rest, we have electric field around it. Means, is it necessary that for you to have electric field, the charges need to be at rest always? Think about this question. So first chapter says electric charges and fields. My question, so it falls under a branch called as electrostatics. But the important question is it always necessary that the charges need to be at rest for electric field to be defined? The answer is no, because if charge exists, there is electric field around it, irrespective of whether it is at rest or in motion. But for you to generate the counterpart of it, which is called magnetic field, what is necessary? You need those charges to be put in an aligned motion, which we called it as electric current. So we understood the fact that the base for magnetism is the electric charges in motion, right? So what did we do in the fourth chapter? If you recollect all the topics and see, right, we would have done only two things. One is, if you have a current carrying conductor in hand or current carrying coil in your hand or whatever it is, we try to understand how much amount of magnetic field it would generate. Because in your 10th standard itself, you learned the fact that electric charges can create magnetism. But to what extent the values will get created is what we saw this year. Is it right? And that is the idea which we took to the fifth chapter also. We understood that wherever charges are in motion, there is magnetism. That is why you had something called as atom as a magnetic dipole. That was the first derivation that we did in the previous chapter, if you are able to remember. Right? Then we tried to understand how a solenoid is similar to a bar magnet. Bar magnet is a permanent magnet, whereas a solenoid is a temporary magnet. We tried to relate both of them, right, with the help of some mathematical expressions. Right? So the whole objective of 5 chapters is telling me that charges at rest or charge itself can create electric field. Charges in motion can create magnetic field. Okay, I understood this. The next question that comes is, why is this chapter named as electromagnetic induction? What are they trying to tell us? Are related. In the sense, in the fourth chapter, electricity created magnetism. Electricity generated magnetism. Now, we know that science follows symmetry. Is the counterpart also possible? Means, can magnetism also generate electricity is what the next question is. Right? But we know the fact from third chapter that if you just have charges, then can you generate aligned motion to it? If you just have charges, for example, this is a conductor, okay? In this conductor, you have 3 charges. But can I say this conductor is going to conduct without the support of something which is connected around it? What do I need to connect? I need to connect a potential source. Means I need to create an EMF. So this chapter mainly speaks about electro refers to charges, magnetic refers to magnetism, induction means creating something. Means it is exactly the reverse process of what we did in the fourth chapter. Means with the help of magnetism, will I be able to generate EMF? What is EMF? Electromotive force. Okay, which is also potential difference for an open source, right? So magnetism, with the help of magnetism, if you are able to generate EMF, then that branch of physics falls under a category called as electromagnetic induction. So induction is generation of something. Is it clear? So try to break the word into different parts. Electro refers to charges. Magnetic refers to magnetism. Induction refers to creating something without a physical contact. So if you are able to create something without a physical contact, you call it as induction. Because we had something called as, if you remember, we had something called as electrostatic induction also, where you take a charged object closer to a neutral object and you create charge on it. Do you remember that? Right? So that is the principle on which capacitors are actually designed. Now, having said this, I need to answer certain questions. Like how exactly is it possible? Means what kind of a system I need to have in the first place to ensure that magnetism is able to generate EMF, for which we will see a small simulation. Then
It's talking about that charges in motion. Four charges in motion. Say magnets in motion.
magnets need to be in motion, but that relative motion with respect to whom is what? With respect to whom? You mean to say if you put a magnet in motion, means you're trying to say that you'll just take a magnet and put it in vibrational motion. Is that what you're saying? If you do that, you want to generate EMF. Can we means see for you to have that EMF, right? You need a source. See, for example, you need to create a charge. Where will you create a charge? You need a source, right? At least to hold it for at least fraction of a second. Without a source, if you keep vibrating, where will you generate? In the air, it doesn't work. So where will you say EMF is generated? Nowhere. Means if that is the case, I can take a magnet and run it like this, and I can say surrounding me I have EMF, which doesn't make sense. How will you test it? Right? So that is why you need to have something. You need to have an electrical device in your hand to do that. That is what I'm going to show you. I hope you're able to see it. So listen, observe this carefully. I'll be asking many questions. Observe. Okay. So what do I have here? I have a bar magnet and a coil which is connected to a bulb. So this is what I told you. If this some testing source is needed. If you observe one important point, I didn't have a open conductor. I didn't have an open conductor. Coil is a closed surface, and the closed surface is connected to a bulb. What is the bulb doing? Bulb is just a testing piece to make us understand whether the electric charges are moving or not. I can replace this bulb with a galvanometer also. That is my wish. Okay, but now you're able to see some dots, right? What do you think those dots are? They are electrons. So you're able to see a magnet around which you have magnetic field. So what is the direction of magnetic field? It is from north to south. You're able to see that shape. Are you guys able to see the shape that is? There is a pattern, right? It goes from north to south. So the red color, that is actually the compass that is placed. When you place the compass, right, whatever direction it means, the north pole of the compass shows is the direction of magnetic field at that point. Is that clear? Now see what is happening is, I'm not able to shut down that. Show field this way, show compass, show field meter. Okay, field meter will tell you how much value is generated at a particular point. See, one thing you're able to observe the pattern of the magnetic field lines. Near the magnet, you will be able to see that compass shape is darker, right? Near the magnet, you're able to see that the compass shape is darker, whereas when you move away, you're able to see it gets dull. Why is it so? So the field strength will decrease because it's inversely proportional to the distance square. Okay. Now when I move this magnet, okay, when I move this magnet closer to the coil, am I trying to take more amount of magnetic field towards it? Can I say that? Means because I know that poles generally have the higher value of magnetic field. Now see what is going to happen. Did you observe? So what is happening? You're able to see a blink, whereas you're not able to see something glowing continuously. Is it right? So what is happening here is, when you take the magnet closer to the coil, you're not taking it slowly. When you give a jerk, when you accelerate it faster, what will happen is, there is some amount of field line. There is some amount of field line through this coil that is getting generated outside, right? You're actually trying to change those number of field lines which are actually passing through. What do you call those number of field lines as? What flux can you call this as? This can be called as magnetic flux. Means if you are able to change the magnetic flux associated with the coil with respect to time, then what you can do is you can generate EMF. But what should happen? It should be a continuous process for you to see the values. Does it make sense? Are you able to understand what you're saying? So that is why I told you in the beginning itself, you cannot use an open conductor. If you use an open conductor, what is the first thing you cannot define at all? There is no concept of flux because there is no concept of area. What does flux tell us from the electric field? What does electric flux tell us? The number of electric field lines passing through a given area perpendicular to it is what is called as electric flux. Similarly, if you are able to define the number of magnetic field lines passing through a given area, you can call the same thing as a magnetic flux. Means if you are able to change the magnetic flux with respect to time, you can generate EMF. Okay. Now comes an important question. Is it necessary that I always need to move the magnet towards the coil, or can I do the vice versa as well? Yes, I can do that because it will still work. Because irrespective of whether you move the coil towards the magnet or magnet towards the coil, one common factor is you are changing the magnetic flux associated with the coil, right? So when the magnetic flux is changed with respect to time, using whatever means you want, you can generate EMF. So this is the basic principle on which generators are defined or designed. See, for example, we are receiving these things, right? You're able to see a light that is glowing, right? When I switch on this one, the light is glowing. Do you think this light is glowing constantly? Or is it appearing as if it is glowing constantly? Do you think it is a constant thing, that is a constant brightness is thrown on you? Is that what you're thinking? Actually, what is happening is it is flickering. But the flickering will be so fast that you will not be observed. You will not be able to observe it. If you want to observe that, you can see it during the times when you have low voltage at your home. You would have observed whenever there is a low voltage, it will start blinking even if it is an LED bulb. Are you able to understand what I'm trying to say? So, where is it coming from? Generally, the source that you have connected, right, that is also an alternate AC source. It is not a DC source. Only DC sources can make something glow continuously, whereas AC will keep changing its polarity. I'll show you how it works. So, if I have a generator, you're able to see this north pole, right? Now, when the north pole is here, there is some amount of magnetic field associated with it. Now, what I'm going to do is, with the help of a tap, I'm going to put this magnet in a continuous rotation. See what is going to happen. Are you able to observe? So when the north pole, when either of the poles is coming closer, the glowing part is high, whereas when it is going away, it is slightly less. But this is how a bulb will glow. Whereas if it is happening this fast, right, you will not be able to see the flicker. So that's what is happening, because it has certain frequency that is associated. Whenever you go to any electrical device and see, right, they would have written the voltage associated with it and the frequency across which it will be handled. For example, if you want any device to work in India, you need to design those devices at an average value, not average value, it's called as RMS value of 230 volt. Have you ever seen the stabilizer of AC with a display? If you have not done it, go home and observe. If at all you have, for ACs, you have a stabilizer with a display, you will be seeing the values varying somewhere between 220 to 240. So why are stabilizers generally used? Name itself is telling you. To stabilize the voltage, right? Whereas you will always have a fluctuation. You can never get a stable voltage of 230 unless it is theory. Okay, somewhere between 220 to 240 it keeps oscillating. That is actually an alternating current. And where is all those things coming from? The logic of electromagnetic induction. That is why it is one of the important discoveries. You can do that. You can do that, but what source do you need to use to increase and decrease? Why do you want to use that? You don't know how many days it will work. Compared, if I give you an option of using a temporary or a permanent magnet, let's think of the real-time scenario. Okay. Let's say I'm asking you to design such that my device is working for 5 years. Which one will you prefer? You will prefer a solenoid or a permanent? You can do it. Theoretically, you can do it. But you need to also look at the advantages of it. Right. So are you guys able to understand what I'm trying to say? So this is the concept on which the whole chapter runs. So there is only one thing throughout this chapter. I'll be speaking about only one thing. What is it? If there is a change in magnetic flux taking place with respect to time, you can generate EMF. That's it. You need not think anything outside that. So wherever they say EMF is induced, first thing you need to observe is where is the coil and where is the magnetic flux changing. Nothing. You need not think anything outside this. Is that clear? So having all these points in mind, let's start taking down the theory part. So first write down the definition of magnetic flux. What is it? Write down the definition of magnetic flux. So how is electric flux represented? What symbol is used? So you write phi B. The subscript is B. So when you use this phi B, how do you define magnetic fluxes? The number of magnetic field lines. Yes, please continue. Number of magnetic field lines. Please write it down. Number of magnetic field lines passing through a given area. Number of magnetic field lines passing through a given area normal to it. Number of field lines passing through what? Through a given area, and how should it pass? Normal to the surface. Okay. If at all I have a coil like this,
area.
You want me to repeat it?
Yes, sir.
So I'm saying the number of magnetic field lines passing through a given area, comma, normal to it.
Yes, sir.
So if this is the area, guys. If I take this to be theta, don't get confused between phi and theta. Phi is the symbol for magnetic flux. Theta is the angle between the magnetic field and the aerial vector. Generally, how do you take the aerial vector? This I introduced in the first chapter. It is always normal to the surface in which direction? Outward direction. So put out two-dimensional surface, it is you are free to choose. There is no rule saying that this is the only outward direction. So phi B another. What can I write phi B as? Can I write it as B A cos theta? Can I do that? Or can I write this as B vector dot A vector? Both mean the same. Right? So if I want to define small amount of flux d phi B, can I write this as B vector dot dA vector? Yes. Right. So if you observe in all the three scenarios, what is going to be the SI unit of it? SI unit is Tesla meter square. This Tesla meter square is also called as WEBER, which is Weber. So it is also called Weber. And what is Tesla equal to? Can I write it as Weber per meter square? Can I do that? So that is why if you see the previous chapter, right, in some of the bases, wherever magnetic field is there, they would have mentioned Weber per meter square instead of Tesla. Are you able to understand where it has come from? Yes or no? Clear? So it is called Weber per meter square. Next is magnetic flux a scalar quantity or a vector quantity? It is a scalar quantity because you are doing the dot product between both the vectors. And moreover, it says it is a number of field lines. Is it clear to this point? Right. Now, the next question that we need to ask is, we define magnetic flux. We understood what is magnetic flux. So, but what is the important phenomenon that we observe with respect to a magnet and a coil? Niranjan, you want to wash your face? Can you try to define it better? If there is, I told you something. If there is a relative motion, So if you observe, right, if you want to change the magnetic flux, by now you would have understood that there needs to be some mechanical system also present. So why am I using the word mechanical system? Is because you see how generators get started. They'll use a wire kind of thing and pull it, and it will start rotating. So you need to do some mechanical work so that you are able to put something into rotation, and that is getting converted to some electrical form. So that is why the statement always goes like this. If there is, listen to this, then I'll give you the statement. If there is a relative motion, when the reason I'm using relative motion is because I can either move the magnet and keep the coil stationary, or I can keep the magnet stationary and move the coil, or I can move both. So in all the three scenarios, there is always a relative motion existing between the magnetic source and the pickup coil which is picking up the EMF. If you see, that coil will not have any EMF source, right? We didn't connect any battery to it. That is one important point to be observed. So for this, there is a statement called as Faraday's law of electromagnetic induction. So whatever statement I gave you was actually proposed by a scientist named Faraday, and it was further named as Faraday's law of, see, the short form of this chapter is EMI. So Faraday's law of EMI, what does it state? Please write it down. If there is a relative motion existing, if there is a relative motion existing between, if there is a relative motion existing between the magnetic source, if there is a relative motion existing between the magnetic source and the pickup coil. Why am I calling it as a pickup coil? Because it is the one which is picking up the EMF. Okay. So I repeat it from the beginning. If there is a relative motion existing between the magnetic source and the pickup coil, comma, and EMF is induced, comma, and EMF is induced. If there is a relative motion existing between the magnetic source and the pickup coil, comma, there is an EMF induced. So I need to give a mathematical expression. By me creating a relative motion, what is happening? There is a change in magnetic flux, right? Actually, I forgot one thing. Can you strike off that an EMF is induced? Sorry about it. Can you strike off that an EMF is induced? So there is a relative motion existing between the magnetic source and the pickup coil, comma, there is a change in magnetic flux. There is a change in magnetic flux. There is a change in magnetic flux, which in turn, there is a change in magnetic flux, which in turn induces EMF. Now listen. So can I say that EMF has something to do with the change in flux? So I will write EMF is directly proportional to the change in flux with respect to time. So what is this called as? This is called as rate of rate of change of magnetic flux. Suppose the coil has n number of turns. Okay. Suppose the coil has n number of turns, then EMF is also directly proportional to, I can say, n. When you combine these two, we can say EMF is directly proportional to n into delta phi divided by delta t. Yes, n is the number of turns in the coil. So EMF is directly proportional to n into delta phi divided by delta t. So EMF will be equal to negative of n into delta phi divided by delta t, where this negative sign, is a significance of a law called as Lenz's law. Negative sign is a significance of a law called as Lenz's law. Is it clear? That -1. That's it. So the negative sign is the significance of Lenz's law. What does the Lenz's law mean? I will slowly come to the point. Okay, I'll slowly explain it to you. But is it clear till this point? Right? If the relative separation between them is not changing, then there is no flux. Sorry, then there is no EMF induced. I hope it is clear to this point. Right? Based on this, we will try to solve some problems. Let's see if this works. You're able to read the question. Are you able to read the question? So there is a square loop of side 10 centimeter, okay, and a resistance of 0.5 ohm, which is placed vertically in the east-west plane. First, you have to imagine all these things. So never read the question completely. First, read it sentence wise. So what are they saying? There is a square loop, and for the square loop, they have given you the side. So what is the side of it? A is equal to, first write it down in this format. Write it down. A is equal to 10 centimeter. Why did they give you the side? Since in this chapter, to find the area of the coil. So if side is given, area is automatically given. And the resistance of the coil is given to be 0.5 ohm. And it is placed vertically in this direction. It is placed vertically in the east-west plane. Okay. Then there is a uniform magnetic field of how much value? So there is a uniform magnetic field of 0.1 Tesla, which is set across the plane in the northeast direction. Okay. Then suddenly, if you observe, the magnetic field is decreased to 0 in 0.7 seconds. If that happens, that's what we need to do in the second. So there is a square loop of side 10 centimeter. Okay, there is a square loop of side 10 centimeter. It is placed vertically in the east-west plane. So what is the east-west plane? So this is east, this is west. It is placed vertically in the east-west plane, and there is a magnetic field in the northeast direction. So this, what is the angle between both? What is the angle between both? It is 45 degrees. Okay. So when it is going to be 45, theta is 45 degrees. Theta is the angle between B vector and A vector. Is that clear? Is it clear till this step? Right. So first take the data, I'll tell you how to solve it. This is like this to vertically placed. Now with respect to your hook, you can take it like this. Area vector is like this. Magnetic field is in this direction. So it is in the northeast direction. Yeah, but vertically in the sense, see, it is placed vertically in the east-west plane. Wait. So it is placed vertical. So this is the east-west plane. Observe, they didn't say east-west axis. They used the word plane. This is east, this is west, and this is the plane, east-west plane. Is that right? So it is placed vertically in the east-west plane. You can place it like this also. Okay, when you place it like this, and there is a uniform magnetic field of 0.1 Tesla, which is set up across the plane in the northeast direction. Yeah, like this. So if you take it in this way, if you take this to be the north, south, east, west, then you can keep it like this. If you take this to be if you take your paper itself, so what he is asking is, in which direction is that northeast I need to consider? Do I need to take it in this direction, or should I consider it in the plane of the paper itself? I repeat the point, listen to this carefully, okay? So you understood the first part. You have a square loop which is placed vertically in the east-west plane. You understood what is that east-west plane? East-west, there is a plane. Right? This plane we have placed. So what is the direction of aerial vector for it? So this is the direction of aerial vector. Okay. Now if you take this to be the north and this to be the south, then what is the northeast direction? Is it not in this way? So this is northeast and this is the north. So what is the angle here? Northeast itself means 45 degrees. So theta is the angle between the magnetic field and the aerial vector. Is that making sense? Right? Yes. So theta is equal to 45 degrees. And see, when you solve these kind of problems, right, it is the most important point is collecting the data in the right manner. So I hope you read the question, right? So what is the value of A? So 6.2, A is equal to 10 centimeter, right? So A is 10 centimeter, resistance is 0.5 ohm. Then B is how much? 0.1 Tesla. This is the initial value. Finally, what happened to it? The magnetic field is a uniform magnetic field of 0.1 Tesla is set up across the plane in the northeast direction. The magnetic field is decreased to 0 in 0.7 seconds. So magnetic field is decreased to 0 in 0.7 seconds. So what is the value of delta T? 0.7 seconds. And what is the value of theta? 45 degrees. Now read the question carefully again. They are asking you find the magnitude. So what do they mean by magnitude? They need only the positive value of it. They use the word magnitude because I gave you an expression. What does that expression tell you? EMF is equal to negative of n into delta phi by delta t. So that negative sign can be ignored. And one more point is, I told you it is n into delta phi by delta t. So how will you choose the number of turns? The keyword is, where is it? The keyword is very simple. If you see the word called as loop, loop is always one turn. Coil is always number of turns. Multiple turns. Loop is always one turn. Okay. So the n value is also equal to 1. I hope you understood the data, right? How to collect the data. Now, we need to find the magnitude of the induced EMF, which is equal to magnitude of n into delta phi divided by delta t. N is 1. Delta phi is how much? B final into A final into cos delta final minus B initial into A initial into cos delta initial. Divided by delta t. So B final is 0. What is B initial? 0.1 into A initial is 10 into 10 power minus 4 because A square into cos of 45 degrees, the whole divided by 0.7 within a bracket. Sorry, within a modulus. Is there any doubt in this? B final is 0. That's why I cancelled it out. See, change is always final minus initial. Anyways, we are taking only modulus, so we are on safe side. Remember, cos 45 is how much? 1 divided by root 2. So 1 by, no, I didn't solve it. Why 100? Oh, sorry. 100 into 10, correct. So 100 into 10 power minus 4. So 1 by root 2, if I rationalize it, can I write it as root 2 by 2? So root 2 is 1.4 approximately divided by 2, which can again be approximated to 0.7. So cos 45 is 1 by root 2. Remember that value 1 by root 2 has an important significance in next chapter, which is approximately 0.707. So 0.7 will get cancelled. This will be equal to 0.1 into 100 into 10 power minus 4. This is 10 power minus 1 into 10 power minus 2, which is equal to 10 power minus 3 volt, or it is equal to 1 millivolt. It is equal to 1 millivolt. Okay. Will you be able to calculate the current for this? So what is the value of current? I is equal to E divided by R. That is 1 millivolt divided by, what is the resistance? 0.5. 0.5 is 1 by 2. So this will be equal to 2 milliampere. I hope it's clear. Right? This is all about Faraday's law of electromagnetic induction. There is another interesting problem also, which is in 6.3. Time is 5:56. Maybe that we will do it tomorrow. Okay. And tomorrow we'll see what is the Lenz law. I gave you the law name, right? Negative sign indicates the significance of Lenz law. For that, again, I need to show the simulation and ask you some questions. It will take some time, which we'll do tomorrow. Okay. Apart from that, it's clear, right? This chapter. So revise it and come. Let's see. Guys, those who are online, I hope you're clear.
Yes, sir.
We'll wind up.
Thank you, sir.